For this problem, you have given a graph. The graph has 4 nodes, 0, 1, 2, and 3. There are certain links between, these are directed links. There are certain links between each of these nodes. Between 0 and 1, there is a link with the weight 100. Between 1 and 2, there is a link with weight 100. Between 1 and 3, there is a link with weight 600. So your task is, actually these nodes represents airports, and the links between them represents the cost of travel between these two travel between these two nodes. So your objective is to find a smallest possible travel cost from the node 0 to node 3. You have, this is your source, this is your destination. So you have to find a path where you will be paying least cost. So if you check this thing, this structure, this graph, you can identify that you can come through this one and this one and this one will not give you the least. If you come this way, you will get the least because you have to pay just 300 rupees. If you come this way, you have to pay 400. If you come this way, you have to pay 700. There is one more clause in the problem. You can travel only up to k hops between source and destination. That means you can take, for this travel, you have this hop number 1, hop number 2. You took 2 hops. It is not allowed. You can take maximum 1 hop. You can either choose this path or this path. So the optimal will be this one with a 300 cost. So how will you go with this problem? You can have multiple approaches, but the best approach is a well-known algorithm called Bellman fold. Bellman fold is like, it will have, it's a kind of optimization, maybe a dynamic programming approach, where all of your nodes will have a cell allocated. The cell will have the lowest price to reach at that node. So you have 0, 1, 2, you will initialize it with infinity. Now to reach at 0, you have to pay infinite rupees. To reach at 1, you have to pay infinite rupees. To reach at 2, you have to pay infinite rupees. To reach at 3 also, you have to pay infinite rupees. So this is tough. You are at source. To reach at source, you ideally have to pay just 0 rupees. This is your first iteration. Rest of them will continue as infinity. Then you go for, you have 5 links. This is link number 1. I will make it A. Link number B. Link tag C. Link D. And link E. You iterate through each of the links and optimize your table. So on your first iteration, you will consider a link A. Link A is connecting 0 and 1 with just 100 rupees. So from 0, you have at 0, you have a price of 0. At 1, you have a price of infinity. When you use the path link A, that value will get optimized into 100, because from 0, you have to add more, just 100 more rupees to reach at 1. The same way, it will update the link 2 as well. That also require only 100. 100 more compared to source. Link 3 will continue as infinity, because there are two way you can reach at 3, either from 2, either from 1. Initially, you have 1 and 2 are at infinity. If you add a 200 more to it, or if you add a 600 more to it, in both cases, it will continue as infinity. This is your L0, 0 hops. Now you used 1 hop. The next should be your target. If you are not reaching a target by 3rd iteration, you cannot go for a 4th iteration, because you have constraint of hops. You have used 1 hop already. Now you have to reach, in the next step, you have to reach at your target. Optimization continues. You will not further optimize 0, because there is no incoming nodes. You had only 1 incoming node at 1. It has already optimized. You had 2 incoming nodes at 2. From 1 to 2 and 0 to 2. The best is from 1 to 2, you have 100 plus 100, it will be 200. But from 0 to 2, it is just 100. So it will continue as 100. So here it will be 100, it will be 100. The 2 will continue as 100. Now to the link 3, you have two paths. You can come from 2, or you can come from 1. Both are at 100, but there is a link cost here. 2 to 3, it is just 200. So 100 plus 200, it will cost you 300 if you are coming from 2. If you are coming from 1, you have currently 100 over there. And you will require an additional cost of 600. So this will cost you 700. So the least cost is coming from 2. It will be 300. That will be updated here. Now you have your final vector representing the distance from your source to your destination by using at most one hop in between. So you can confidently choose the 300 as your answer. Now let us see how to program it. That will give you more clarity. So you have the number of nodes here. You have the edges, the flights available from one node to another node, the cost of the links, ideally the links. These links are defined like source, destination, and its cost. And you have your source, you have your destination, you have the number of hops you can use given as k. Define that distance vector, initialize it with infinity. Now you can mark your source as 0 distance because you are starting from source. This is the step. The next step is your iterations. You can have k plus 1 iterations, I equal to 0, I less than or equal to k, I plus plus. You can have k plus 1 iteration. At each iteration, you need current copy of your distance vector so that you can make a second copy for optimization, for storing optimized values. So we'll create a copy of your current distance vector. Now go for optimization. Just flights. So copy of E of 1, this will be your target, is equal to min of copy of E of 1, comma, your current distance, your current source distance, E of 0, and the link weight. This will give you an optimized result. You have to replace for the sake of next iteration or for recording final answer, you have to replace your current distance with your copy. Finally, once you did all the iterations, you will have optimized value populated in your distance vector. So check whether distance of DST equal to int max. That means after k hops, the flight has not reached at your target, then return -1. Otherwise, return destination, distance of destination. This shall work. Let's test. It gave negative something. So there is some problem with see, it might be overflowing. That might be the reason. So we can have some bigger value. The problem will have some constraints for upper limit for your value of the weight of the edge. So if you keep int max, maybe it will overflow and it will go to negative. You can have a lesser value than int max and try the solution. Yeah, it is giving the correct answer. So you cannot use highest value of int. You can use some smallest value of int. You can look at the constraints and you can plan according. This is giving the right answer. Thanks for listening.